Hey everybody, and welcome to episode 53 of the iPhreaks show. This week on our panel we have Andrew Madsen.
Hi from Salt Lake City.
James Zuber.
Hello from Minneapolis.
I'm Charles Max Wood from DevChat.tv, and we have a special guest this week, and that's Colin Cornaby.
Hi from Portland.
Do you want to introduce yourself really quickly since you haven't been on the show before?
Sure, yeah. I'm an iOS software developer currently. My background, I did shareware when I was younger, so I was on the Mac platform a little bit, but my academic background is I actually went to school and worked on a lot of multi-core GPU sort of based programming. And then I actually ended up I work at a company called Digimarc right now. We do augmented reality sorts of stuff on iOS. So it's a nice dovetail of that stuff back into mobile because I get to work on really computationally intensive stuff on mobile devices and really optimizing that out.
And so if you want to optimize something on mobile, you just write it in C, right?
Yes, that is totally that's not yes, C will get you a little bit, but no, that's not necessarily where you go. Yeah.
So you want to give us a brief introduction on how to think about this stuff?
Sure. Yeah. So mobile, you're a little bit more limited than your choices on the desktop. I'll start with, where you typically start on the desktop is, on the desktop, the two paths that you kind of have right now are, CPU-based optimizations and GPU-based optimizations. And GPU-based optimizations are still kind of developing. Part of the problem when you're looking at GPU versus CPU is GPU is typically on the other end of a, PCI card, and you've got to transfer all this data over the card and then do your computations, transfer the data back, and that can take some time. So a lot of people these days will the layperson will say there's a lot of interest around, GPU-based optimizations, and the path there isn't so clear. On CPU-based optimizations, the path is really clear. You've got multi-core. You've got something called SIMD, which I can talk about, which stands for single instruction, multiple data, which kind of lets you work on big chunks of data. On iOS, the path is a little more clear because you don't have tools like OpenCL available to you. So you're likely looking at CPU-based optimizations. iOS is on OpenGL ES 2.0 right now, but the 3.0 spec has some stuff in there that kind of relates back to OpenCL as well. But OpenCL is a framework that lets you take a GPU and run general computations on it to crunch your data instead. So, but again, you don't have that in iOS. I'm hoping maybe this year at WWDC they'll announce OpenCL for iOS, but you never know.
So maybe we can back up a little bit. Can you tell us a little bit about kind of the differences between GPU and CPU optimization, like a high level of what the difference is and like when you might want to use it, one versus the other? Sure.
So it really has to do a lot with how they were designed, is that CPUs, traditionally they started as, single core processors and they moved up to dual core and quad core, but they were really, designed for working on they're designed for, the way most of us program is they run a program in linear order and they go through step by step and they run on one thread of execution. And even a multi-core machine, we can talk about that, but you might have several threads of execution going. GPUs were designed quite differently where a GPU is built for an entirely different purpose. It's built for getting pixels out to the screen. And you're going to have probably at least a few 100,000 pixels, probably more, on your screen. So when they built a GPU, they built it to, compute all these pixels, as many pixels as they could at the same time. So you've ended up with these GPUs that actually have a few thousand cores on them. They're very small cores. They're not very computationally complex. So you can't do, big programs on each core. But if you can split your data up into thousands of parts and you can actually run little programs on, each bit of data, the GPU might be a better option. So I'm trying to think of an example here. Usually, like say you have an image, get something the GPU is good at, and you want to, adjust the color in the image, you might take the image, send it into the GPU, and then each little core on that GPU will take one of the pixels of the image, do the adjustment, and then send the image back. So those are sorts of things that a GPU is good at. A CPU is typically better, like if you have larger chunks of data that can't be broken up into smaller chunks and you need to run very intensive operations on that data. I'm trying to think of another example here. Something like unzipping a file. That's going to be larger chunks of data. That's going to take a little bit more computation. So that's much better for the CPU to do.
So CPU is more of a general purpose, can handle larger body of work with kind of more complex instruction sets. The GPU is going to have a bunch of different processors that do a little more focused. Is that about right?
Yeah. And again, it really comes back to if you can't break your data down into small enough chunks for the GPU to, operate on and with little tiny operations, really the CPU right now is still your best bet. There's this other cool technology that I can talk about. It's called SIM. So it's single instruction, multiple data. It's what it stands for. It's a complicated acronym. Basically, if you think about the case we talked about with GPUs, where maybe you have a lot of little tiny bits of data, like an image with a bunch of different pixels or something, and you want to do something like, color correct the image, and you got to take each one of those little pixel values and change it a little bit. There's an instruction set on CPUs, which appears a bunch of different places, that can actually help you with that as well, called SIMD. Each processor vendor has their own version of SIMD. Back in the day when we were all on PowerPCs, they usually called this, AltiVec or Velocity Engine, depending on what day of the week it was. And Intel calls it SSD. They have a newer version that has a newer name that I don't remember. But on Neon or on ARM, where I spend most of my time, it's called Neon, and it's a special instruction set where normally when you work with a processor, you're thinking about your code linearly. Maybe you're going through an array and you're, multiplying every value by 2 in that array. You're probably going to have a for loop where you loop on through and you multiply every value by 2. SIMD is this really interesting instruction set where you can actually take entire chunks of your array, load them into the processor, and the processor is going to, with a single instruction, do whatever math you need to do on those, multiply them all by 2 or add a number or something like that. Where you commonly see this used is, if you're working on audio, maybe need to adjust the volume of an audio clip, maybe need to double the volume. When you double the volume of an audio clip, you're going to go through the audio clip and multiply all the values in the audio clip by 2. So you might use SIMD for something like this. Now, unfortunately, SIMD traditionally has only been available as assembly instructions. And worse than that, there are different assembly instructions for each processor type because, ARM, like I said, has their own Neon flavor, and PowerPC had AltiVec, and Intel's got SSE. And so typically, if you're a Mac developer, you've got to write out the assembly for each platform. But Apple has done us all a favor, and they have this framework called Accelerate, which everybody should go check out if you haven't checked it out. It's a great framework. It's written in C, so it's a little hairy. But it's this great framework that basically Apple's written the assembly code for each platform for you, and they've got a bunch of common functions you might need to do with this technology. And to you, they're C, but they've actually been written with the proper, well-optimized backends. And if you use Accelerate to do these things, it has DSP functionality, matrix math functionality, all that fun stuff you might need if you're doing really technical things. You can use this framework over all your processor architectures, over the Mac, iOS, everything, and you'll be able to take advantage of all these significantly faster functions. One place I actually ended up using this the other day is for image scaling. They've got a really good image scaling function there. So if you're writing an app that does a lot of image scaling, you might find that the UI kit, UI image methods are actually a little slow. So they have a really good scaling routine in there. You need to get Accelerate is a C-based API, so it doesn't understand UI image natively. So you need to do a little bit of translation work there. But once you've done that, it's got a really fast scaling routine and a really fast rotation routine that you can use to do all that work really fast and then bring your image back into UI image and push it into your UI wherever you need it. So that's an example of one thing I used Accelerate for the other day.
Okay, so you got image processing. I've also seen people use it for digital signal processing. They're trying to do the fast Fourier transform, a lot of math stuff. What other things that maybe aren't as special interest that maybe a regular developer might also find useful?
Yeah, so fast Fourier transform is a good example of something that's a little more technical, but is also there. I've seen a lot of people write that by hand, and I'm like, well, it's in Accelerate. You don't have to write it by hand. But I think the most common example is if you have arrays of data and you need to just do a mathematical operation on that data, you need to multiply it all by 2 or something. I'm trying to think of a general example where you need to do that, but we've all run into that sort of situation where you get an array of numbers and you need to add 1 to them or subtract 1, or maybe you need to correct for they're referencing some index in an array and you need to correct that sort of thing. So
that'd be typical for like an audio application. You're trying to create a volume control.
Yeah, an audio application, that sort of thing. It really is, if you've got arrays of numbers and you need to do any math to each value in the array, which could be a lot of situations, it might be an API to look at. The downside of Accelerate is it's very picky about your number formats. So if you use the raw assembly functions, you can get away with a little more. But Accelerate, because that's to be generalized, can be very picky about, what formats and numbers you bring in. So some functions only say, I'll work with a float. Some functions only work with an int. And you may have to convert your data between, different bit depths of data formats. So that is the one downside. So it's not necessarily a slam dunk in all situations, but if you have some operation you do over an array of data, you might take a look at it. And if your data format matches cleanly with a function already in Accelerate, it could be a really viable option for, an application. Image data, it's also particularly picky on. I had a image come back from the camera that was in this special format, and Accelerate really only wanted RGB data, which makes sense for a lot of people, but you do have those corner cases where, image data as well may not fit cleanly into Accelerate. You've got to, do a little bit of overhead to convert the image into a format that Accelerate wants.
We need an Accelerate for Accelerate, I think.
Yeah, another set of APIs to get everything in the right data for Accelerate. Yeah, that would be great. So I also do Android programming on the side, and we're actually, if this technology, works for your application, we're really lucky to have it, because on Android and on other platforms, there isn't very much like Accelerate. And it's kind of this toy box where, it's been hidden off in the corner and there's a thick layer of dust over it, and, everyone's kind of forgotten about it, but it's over there. And if you open it, there's tons of great toys in there to make your application run really fast. But no other platform really has this toy box. There's a few third-party APIs for Android that are kind of starting up trying to build something like Accelerate. But really, it's kind of this hidden treasure trove of functionality that not many people know about. But it's one of those things that when people know about it, it makes iOS a really great platform.
Yeah, definitely. I met a developer who was working on a piano tuner application, and when he started working on the application, I don't think Accelerate was available yet, so he ended up writing all his routines by hand, which, they're kind of known algorithms, but you don't need to do that. So it's very cool, very powerful to have it all there under.
Yeah, I mean, not only does it, it does make your application faster, but it saves you a lot of time, because, like I said, with the FFTs, the fast Fourier transforms, you can write your own. You can go on Stack Overflow, and there's a lot of threads on, here's the algorithm you should use. You can write it in C. Not only are you going to have to write it yourself, but it's going to be slow because it's going to be in C. Meanwhile, there's these nice built-in methods for doing them really fast using these special instruction sets. So,
I'm curious if you can talk a little bit about it, to talk about how OpenCL sort of fits into the whole picture, because I have this vague idea that OpenCL is sort of a API where you can write, I guess it's really sort of almost like a language, even though it's C-like, is that right? But you can write stuff, and then it can run on the GPU, but it may fall back to the CPU depending on the hardware you're on, and you just don't have to worry about that. But I don't really understand what it can be used for, and in what ways it compares to Accelerate and differs. And so if you could talk about OpenCL, I'm certainly interested in that.
Yeah, so I'll back up a bit. There's two competing standards out there right now. There's CUDA and OpenCL. Both are kind of efforts to, so CUDA is a framework and a language that is specific to NVIDIA GPUs. And it all kind of started with CUDA. CUDA was actually where I did my first work on GPU sort of programming. Basically, what you're doing is you're writing a little program. If you've worked with OpenGL shaders, I don't know if anyone here has, but if you have, they're kind of a similar concept where you're writing a little tiny program that's going to get uploaded to the GPU, and it's going to get run on each of the little processors in the GPU, which again, these days is thousands of processors. So you can take this little tiny app and upload it to the GPU and put it on these thousands of little processors. And then you load data into the GPU, and these thousands of little processors are going to run on your data with your little app you've uploaded, and basically chew on your data and send it back to you. It's going to have, altered your data in the way the program wants the data altered, whatever program you've written. So CUDA was NVIDIA's effort to do this with their GPUs. They had this framework, and it was specific to them, and it helped them sell a lot of, NVIDIA GPUs. So Apple, with, several other companies came along and they said, well, that's great, but we have a lot of different kinds of GPUs we're shipping, and we don't want to have this technology specific to NVIDIA GPUs. And back then they shipped a lot of GPUs that weren't actually very good as well. You had a lot of not very great Intel integrated graphics chips they were using. So they really wanted something that would run really well in the CPU as well. If you wrote something in CUDA, typically you'd have to write it once in CUDA and then write it once, in C or C++, so you could actually run the same functionality on machines that didn't have NVIDIA hardware. So having a CPU fallback was, very important to these companies, because if you didn't have the right hardware, they didn't just want the program to stop working. You had to be able to run these apps on machines that didn't have any GPU at all that was reasonable. So everybody got together, AMD, Apple, and they came up with this new standard called OpenCL. And the idea behind OpenCL is you're going to write, it's a very similar thing where you write these tiny programs, sometimes called, kernels, and they get uploaded to the GPU. The OpenCL language is a little different. The other big difference of the OpenCL is the little programs you're writing are actually getting compiled when your application's running. Typically when you write an application, you compile it, in Xcode before you ship the application. Under the OpenCL model, typically what's happening is your app is running on the user's computer, and because you don't know what kind of hardware they have ahead of time, their computer is going to take it and say, okay, I have an AMD GPU, or, I don't have any really decent GPU at all, I've just got an Intel CPU, and they're going to take your program on the fly and compile it for the right architecture.
Kind of like a just-in-time type of thing.
Totally just-in-time, yeah. That's exactly what it is.
Is that even available on iOS?
It is not. Well, so I had an interesting experience the other day where, no, publicly it's not available on iOS, but I was doing some core image work the other day, and apparently I put core image in a really weird situation, and core image started spitting out OpenCL errors at me. So I was like, that's interesting. So it seems to be there. We don't have access to it, but Apple seems to be using it for the core image backend. And definitely the processor architectures Apple's using have advertised OpenCL support. So the hardware they're using is supposed to support OpenCL. The framework is definitely there on iOS. It's not publicly available. My guess is because OpenCL is in its nature a just-in-time compiler, Apple may not feel great about having, just-in-time compiles happening on iOS devices. You kind of see that with WebKit, where WebKit has a just-in-time version of JavaScript, and iOS applications don't get access to that either. I think Apple's very worried about security concerns around just-in-time compiles. I did see there's a new version of OpenCL, which I believe, again, because OpenCL is not on iOS. I don't do any of my day work in OpenCL, but I saw there was a new version of OpenCL that's supposed to let you compile to some mid-level language, and then it'll do just-in-time compile from that. So maybe that'll make Apple feel better. I'm not sure. It may end up that we may never see OpenCL on iOS. I hope it happens. But if Apple's worried about the just-in-time nature of OpenCL, they just may never ship it. So,
well, and OpenCL is not the first or only thing that's on OS X and also on iOS, but private on iOS. I think XPC is also on iOS and yet not exposed publicly, so they don't seem to really have a problem with keeping certain things for themselves, but I hope we see it someday too.
Yeah.
There's nothing stopping from people. The main problem with the just-in-time thing is, they don't want their apps shipping with that, but if you're doing something like Enterprise or doing something out of the App Store, there's a little more flexibility with that because they're not checking that type of stuff.
Yeah. There was actually a really interesting development that happened around people trying to get around these OpenCL, or OpenCL not being there is, so I mentioned earlier that OpenGL has this concept called shaders. And shaders are really the exact same concept where you're writing a little program, but instead of being designed to operate on raw data, this little program is designed to operate on pixels. But people said, we've got OpenGL and shaders on iOS, and I could probably represent the data I need to compute as pixels. I could not really trick OpenGL, but misrepresent what OpenGL is actually working on, and I can take my general data, pretend they're pixels, shove them into OpenGL, and write a shader to actually do computations on my data. And that actually, I think there's a few example projects out there. I can probably go find one, but there were a few people who actually did it and demonstrated this works, you know. You can do the same sort of stuff OpenCL does, but write it as OpenGL and pretend your data is pixels. And it looks like so the current version of OpenGL is OpenGL ES 2.0 on iOS. Is it 2.0? No, it's 3.0. 3.0 is the current version. The new version is 3.1. I always get my OpenGL numbers confused. So 3.0 is the current on iOS. 3.1 actually includes this bullet item called compute shaders. So it looks like what they're doing is they're taking the hack that people were using on iOS of pretending their data was pixels and throwing it into the GPU and having the GPU do all the work on it. And they're actually formalizing that hack. And they're saying, we're also going to have a just general computing component of the OpenGL ES standard. On one hand, that's great because that means, if Apple adopts OpenGL ES 3.1, we can do general computing on the GPU just fine. On the other hand, that makes me sad because it's yet another standard, and I'd rather just write my code once and have it work everywhere, and OpenCL seems to be the best way to do that. So it still makes me sad that there's no OpenCL on iOS because I'd rather be using that instead of some OpenGL ES extension.
So do you have examples of things that you've optimized using these techniques? Like specific programs that you've worked on?
Yeah, well, most of my work has been on iOS recently, and again, there's no support on iOS. Back on the Mac, I used to work at a company that did a lot of they did Final Cut plugins, After Effects plugins, that sort of thing. And that's really where you'd want to start taking advantage of that stuff. Back in that time, GPUs were still a new thing, but they were experimenting with GPU-based computations. So there was a lot of, again, image adjustments, that sort of thing. GPUs are really designed that was the basis of their design, is to take images or 3D graphics and do just a bunch of pixel computations at once. So typically that's where you see a lot of GPU work going right now is, I've seen a few projects that are just starting to get into, let's take audio buffers and put them on the GPU and see if we can, change them or adjust them or do effects. But still, most of the time you see this sort of work done, it's on images. There's also a few other projects out there that are trying to use it for other purposes. There's a few of those, like the Folding at Home client, I think, might have an OpenCL version. There's a few of those sort of projects out there that are trying to tap into GPUs. Bitcoin mining, apparently, is big on GPUs. I don't know much about that. Don't know much about Bitcoin in general, but I've heard a lot about Bitcoin miners using GPUs. It's probably OpenCL, I'm not sure, but I'm guessing that's going to be OpenCL they're using.
I think at this point, the only way to make money with coins is to use a kind of GPU-based solution.
Right.
Because the CPU-based ones are so processor intensive, and it takes so much energy to make it that you don't actually make any money. But if you have a really serious GPU setup, you can actually efficiently mine the coins and do the transactions.
Right. Yeah, I think it's actually gotten even worse than that. Now people are using custom ASICs that are designed just for Bitcoin mining, which seems completely crazy to me that got big enough that it was worth it to design custom silicon to mine these things, but that seems to be what people are doing now.
So I've been trying to mine Bitcoins with the Beowulf clusters of iPhone 4s. I don't know, am I doing that right? Is that going to work?
I think it would have worked 3 or 4 years ago, but not anymore.
Oh well, all right. Back to the drawing board.
So I think one reason you don't see GPUs used more often as a general technique is because, as I mentioned earlier in the podcast, when you're talking about CPU optimizations, your data and the CPU are very close. You've got your RAM and you've got your CPU, and it's very easy to take your data out of RAM and put it into the CPU and do all the work you need, and then store the data back into the RAM. Typically, a lot of GPUs, especially on desktops, are on some sort of PCIe card. So if you just look at the raw mechanics of getting your program and then your data into the GPU, you've got to pull it out of RAM and then send it over the PCI bus into this card, which takes a lot of time. It's not a lot of time, but as in computer time, it takes a lot of time to get it over to the PCIe bus. And then you're going to run your program on the graphics card, and then your graphics card typically has to send the data back. Now, if you're working on graphics, which again, people are typically working on, you don't have to send the data back because the next destination for that data is actually going to be the screen. So that makes things really easy on you. But if you're trying to do general work, you've got to send that data back to the CPU because you're going to need to save it in RAM or save it, to the disk or something. So that's the other reason you don't typically see the GPU workflow still used as much as CPU optimizations, because you got to do all this work of sending your data up to the GPU and getting it back, which takes time. That is something that is changing. And actually, that's changing courtesy of integrated graphics, where integrated graphics, your GPU is not on a PCI card on some other end of the system. Your GPU is actually right next to the CPU on the same chip. And if you look, I did a research project back in school where I had one of those old MacBook Pros where I had a MacBook Pro. It had the integrated 9400M card and the discrete 9600 card. I think it was the first time Apple had two graphics cards on a laptop. I don't know if anybody remembers those machines, but you couldn't use both cards at the same time for OpenGL, but you could use both cards at the same time for CUDA. So I had an experiment where I had a set of data and I split it in half. And I sent one set of data to the 9400 card, and I sent one set of data to the 9600 card. And I figured this will be a great experiment because the 9600 will be faster because it's a faster GPU. And surprisingly, the 9400, which is the integrated GPU, which I thought would be not great, was actually the faster GPU. The reason is because there's much less effort in loading that data onto something so close to the CPU. So you look at newer machines, if you look at like the benchmark scores, something like the Iris Pro, which is the new integrated GPU Apple's using in their machines, the Iris Pro typically has better OpenCL benchmark scores than the NVIDIA discrete cards that the new MacBook Pros come with. Part of that is because NVIDIA is not well optimizing their OpenCL right now. So part of it is just NVIDIA is bad at OpenCL right now. The other part of it is because the work you have to do OpenCL with an integrated processor or an integrated GPU is much less. And you're starting to see that in game consoles as well, where game consoles have moved to integrated GPUs as opposed to discrete GPUs, not just for cost reasons, but because there's actually a lot of potential performance there if you bring your GPU closer to the CPU.
So, Colin, I wonder if you could walk us through what are the steps involved to actually test two different cards or chips? I mean, how are you doing that? Are you writing these in C? What's the process for that?
Yeah, I mean, typically what you just do is, you have a switch, what I did back in the day was you just, have two cards. You'd have a file somewhere that would say, gee, I want to test on this card and this card, maybe both at the same time. These days, typically what you do is you have, an automated testing infrastructure where, like, for example, we do at work a lot of, not GPU stuff because it's not available on iOS. We do a lot of SIMD, Accelerate, raw neon assembly, that sort of thing. And we're very curious about how that performs over the different Apple architectures. So we'll typically do, automated testing through Xcode CI, where we'll say, first we want to verify that, these routines are actually running fast on each processor architecture, and we didn't miss something and one of the processor architectures runs slow. The second important thing when you're writing all this computationally intensive code is to verify your results are actually correct. It may be great that you've written this highly optimized fast routine, but if your numbers coming out the other end aren't correct, it doesn't buy you very much. You've gotten the wrong answer very fast as opposed to the right answer very slow. So we also have, rigs that will verify correctness and that sort of thing.
That's very cool. So that's a different setup for kind of Xcode CI than what we usually hear about. We usually hear about, writing unit tests, but using it to actually run tests on different hardware. How does that work? Or how's that working for you?
It's working pretty well. There's a debate in the continuous integration sphere on iOS currently, it seems, between Jenkins and Xcode CI. And we're still using Xcode CI. Xcode CI seems to be a very, 1.0 product still, where every once in a while I'll come in the morning and the testing rig will be, have stopped on a test. I'll just unplug the device and plug it back in and it'll keep going on its way. But the nice thing about Xcode CI is if you're in this sort of situation where you need to, because at work we have a larger office, so we have a core technologies team, we have an applications team, And I'm on the application side, so I'm doing the higher level optimizations. I may just say, I've got these two SDKs and I need to do multi-threading or something between them. But on the low end, they're writing all sorts of assembly and gross stuff. But I may need to get feedback to them that, gee, your assembly is running great on this 32-bit machine, but on the 64-bit, newfangled iPhone, it's not working great. And the great thing about Xcode CI is that it gives you very clear reports, and they're web-based as well. They have an Xcode integration component, but there's a web-based component as well. So you can just grab a link out of your web browser, send it over to the other team, and go, hey, look at this test. Either these tests have failed because probably something's wrong with this algorithm, or, it's not performing very fast. In Xcode CI, there's no timing data as part of the reports, but you can also pull the raw logs out of Xcode CI, the raw testing logs from your unit tests, and they'll actually have the timing data in there. And we do have certain tests rigged to time out after a certain amount of time. So we'll say this test should take no longer than 20 seconds. And if it does, something is severely wrong. So we're going to, just fail the test after 20 seconds. So we do stuff like that. But correctness is also a big part of what we do. The background of what we do is we take basically images, or packaging is our new thing, and we can embed something like an invisible QR code right on top, where we're taking the image and we're very quietly changing values of certain pixels in the image. So if you change these pixel values very subtly so the human eye can't see them, we can embed a pattern in the image that then your phone can see, or a checkout machine could see in the case of packaging. So it's basically like an invisible barcode is right on the top of your image. So for, high performance computing, the easy connection there is that, we have to embed these images very quickly. We have to read these images very quickly. So we have both algorithms that are going over these images, trying to put the signal in, and then we have algorithms that are looking at this image, trying to take the signal back out. So in that case, you have a very clear set of test data. You've got these images with the embedded signal for reading, so you can push them into your server, and you can run the algorithms on these phones that are slave to your testing server, and it can come back out and say, okay, on this phone I was able to find the pattern, on this phone I was able to find the pattern, on this one I wasn't able to find the pattern. The other great thing is not only do we have this Xcode CI server, we have a robot hand downstairs, which is great. It's in a room somewhere. I got to play with it when they first bought it. But the other important thing is that, when you're trying to read these images, if you're scanning them in with like a flatbed scanner, that's easy. You're only looking at them from one perspective. But if you've got the phone, you can be holding the phone at all sorts of different angles over this image, trying to read it. And so not only do we have to evaluate for correctness in all these algorithms, we have to evaluate for how hardened these algorithms are. If we look at it under low light, if we look at it under bright light, wrong angle, right angle, do these algorithms still work? The assembly we've written in, SIMD and Neon and all this other stuff. So as if it wasn't complicated enough to optimize it, you've got to make it really, an aggressive algorithm that will find this pattern. So we have this robot hand downstairs, and the robot hand has an iPhone in its hand, and the robot hand just goes all sorts of different angles, and it moves the phone trying to read the image. That's a more complicated automated test that's run, where it's actually got an app on the phone that's watching the results, sending them back over the network to a server, and then the server is collecting the results, and we end up with a heat map that says, I think it's a heat map organized by like angle and light intensity and stuff like that. And it gives us a nice spread of, okay, this new algorithm you wrote reads less well than the old algorithm, or reads better than the old algorithm. So not only are we in a situation where we have to write these fast algorithms, they have to work under all sorts of obscure circumstances.
That's like CI to the extreme. I'm glad you're having success with the Xcode version of it. I've had differing reports, but it sounds like you guys are doing some things pretty cool with it.
Yeah, our problem, I have two big problems right now with Xcode CI, and I would still choose Xcode CI if I had to choose again today, but my two big problems are, again, as I mentioned, every so often the unit tests just stop, and the server's fine. I mean, the server's not testing on any new devices, but the server itself isn't locked up or anything, so usually I'll come in the morning, one device will be stuck, and I'll just unplug it, and the server will continue testing.
Of course, that never happens with Jenkins,
Yeah, no, so we do have some Jenkins rigs deployed. So we have our raw level tests that test our algorithms through unit tests and things like that. Because we ship applications as well in the store, we have higher level tests that are validating strings and buttons and transitions, that sort of thing. And Apple has two testing technologies for that. They've got the lower level unit tests, and they've got this higher level thing called UI automation, which is really great. Jonathan Penn, who I think, has he been a guest on this podcast?
Yep.
Yeah. Okay. Yeah. Jonathan Penn works with it, and it's really great. And we have a QA engineer who writes all these tests. They're all written in JavaScript, and they'll go through and it's basically an automated person using the application. We'll go through and it'll click buttons and it'll verify all sorts of aspects on your screen. Great technology, not supported at all by Xcode CI. I don't know why, and we have complained to Apple about it before. Xcode CI only does unit tests. And they're both Apple technologies, so, UI automation is part of the instruments package, and unit tests are part of the Xcode package. So we have to run those not through Xcode CI. So we're working on a secondary service to do that. But as you kind of hinted at, Xcode CI is the only testing tool that has been officially sanctioned by Apple to load apps on devices and test. So Jenkins has its own flavor of weirdness where it's using, I always forget the name of the tool. I think it's called Fruitstrap. I think it's what it's called. It's a tool called Fruitstrap, which is basically someone's attempt to reverse engineer how loading apps onto an iOS device work. So it's this tool that Jenkins uses to load apps on devices and test, and we've had varying degrees of success with Fruitstrap. So Jenkins comes with its own issues. It's kind of a shame because there is no 100% bulletproof testing framework for iOS right now. I wish there was, but Xcode CI, I think, is still... With Xcode CI, you get cleaner reports. Your data is formatted a little nicer. The front end's a little nicer. It's actually sanctioned by Apple to load apps onto devices. So I'd still probably go with Xcode CI, but yeah, Jenkins and Fruitstrap are out there as well.
So one of the things you talked about earlier was GPU optimization and breaking down your problems so they can be solved by a GPU. How do you do that? If I've got a problem set I want to solve, and I think maybe I can get performance benefits from going at the GPU route, how do you start breaking down your problem? Do you use Objective-C? I mean, does it help you with that, or how do you do it?
So Objective-C, there isn't much at all in Objective-C for these sorts of performance improvements right now. They're all C-based. So that's the first part of breaking down your data. Is typically, we're talking about running these operations over arrays. An NS array, isn't going to cut it. You've got to have it in a pure C array. So, aside from that, usually you can hope that your data is kind of naturally broken down into small parts you can work on. And that's really why, stuff like multi-threading on CPUs is alive and well, because there just are some problem sets you can't break down. Again, typically the use cases are if you have something a piece of data that's just naturally in a bunch of small pieces. Images, are still the go-to example. You got a bunch of pixels. Audio is another example. You've got a bunch of audio samples, and you might have an audio file full of audio samples, and you want to take all those audio samples and do something to them. I mean, there's a lot of cases where, you have arrays of data, indexes, that sorts of thing. Maybe you've been doing something like a Excel worksheet does, where you've got a table of data and you need to do a bunch of operations on a table of data. Probably should be a big table of data if you're going to be sending it over to a GPU, because again, you're going to take the hit of sending something over to the GPU. But if you have a really big table of data, it might be worth it. I haven't really talked about it, but there is, of course, still traditional CPU multi-threading available to you. Is that, a CPU doesn't have thousands of cores, but these days, if you're on iOS, it has 2 cores. If you're on the Mac, you have anywhere from 4 to 12, still on down to 2 cores to work with. And so if you can't break your data into thousands of little chunks, you might, just say, I'm going to break it into 4 or 5 chunks, and that makes a lot more sense for me. And as well, you don't have the overhead of sending your data up to the GPU. And the good news is, in that case, there's Objective-C ways of doing that available to you. There's also Grand Central Dispatch, which is a C API, but it's still pretty close to the ease of use of Objective-C. Grand Central Dispatch is another really great API that is on iOS that if, people haven't checked it out, they should check it out. It is intelligently aware of, how many cores are on the machine you're on. And you give it a problem set and you say, it's really great because there's stuff like just drop-in replacements for loops. If you have, a for loop in your code and it, could potentially get really long, like maybe it goes up to, you do a few dozen iterations, hundreds of iterations, thousands of iterations. Grand Central Dispatch has a drop-in for loop replacement function for you that will say, this for loop, take the contents of this for loop, and instead of running it on one core over and over again, break it up for me and run it over all the cores on this processor at the same time. So Grand Central Dispatch is, again, something unique to Mac and iOS, and it's very handy for if you have a problem set it doesn't necessarily break itself up into small enough pieces to justify using the GPU for, but is breakable into chunks that you could split over a CPU.
Do you have to break out the chunks explicitly, or does it kind of guess it for you, and how can you provide more hints?
So at least when I've worked with GPUs, both GPUs and CPUs will split it out for you. The one exception to GPUs is if you bring multiple GPUs into the equation. Typically, if you want to use more than one GPU at a time, you've got to do the splitting yourself. The GPUs aren't going to talk to each other. You've got to actually take your data, break it up into chunks, send to each GPU. That's a rabbit hole to go down, though, is multiple GPUs for OpenCL. But for both just single GPU OpenCL and Grand Central Dispatch or libdispatch, it will break it up into chunks for you. And the great thing, again, about Grand Central Dispatch is based on how many cores you've got on the hardware or other conditions on the system, it will choose the best chunk size for you. So it's going to do all that optimization. So you don't have to worry about, do I, want to do 2 or 3 chunks of data inside this for loop? Do I just want to have every single loop work on it? It does all that for you. So definitely, if you're a beginner and you're just starting to get interested in these technologies, Grand Central Dispatch, if you're not already using it, which if you're an iOS developer, you really should check it out and be working with it in your workflow. Grand Central Dispatch is probably the first solution I'd jump to. Those will be the easiest low-level optimizations to make. And then really at that point, it becomes a choice between Accelerate and the GPU. And again, if you're on iOS, that's an easy choice because there is no GPU computing. So if you're on iOS, Accelerate is your option. If you're on the Mac, if you can break your data up into, and it's been a while since I've looked at benchmarks on what the optimum chunk size is, but if you can break your data up into a few thousand chunks at least, the GPU might be a better option for you.
Very cool. So we've talked about kind of the problems in high-performance computing. One of them is like parallelization, be able to split up your algorithms. We talked about keeping things closer on the actual hardware, so moving data back and forth is less time-consuming. Are there any other avenues that we haven't talked about?
Yeah, those are really the two key problems with parallelization. I think there's another problem we haven't hit quite yet, but will hit us in the future, is that one of the reasons we're looking at, parallel processing is, and one of the reasons that developers should look at parallel processing is because if you take a task and you put it on one core of a CPU and it maxes out that CPU core, so you're taking the CPU to 100% on one core, the energy drain for doing that is quite substantial. So I think what's commonly said is that energy usage as you use more of the CPU is, exponential. That, basically on a very simple level, and this may not be the exact numbers, but very simple level, if you get 2 times the performance, you're going to get, 4 times the energy usage and heat output. So if you're ramping up a single core, you're going to be dramatically increasing your energy output. So it's better to split a task over 2 cores running at 50% than it is to max out a single core. So that's typically why we see this model exploding, is because Intel or Apple or whoever's making the processor is able to get a lot of power savings by, instead of making these CPUs clocked higher and higher, just add more cores. Because 2 cores is only going to be double the energy usage of 1 core. You get back to a linear relationship instead of an exponential relationship. Now, the problem is, in order to split your code up to run over these different cores, you have to write more code. Like, either you're writing the code or Apple's written the code and Grand Central Dispatch do that for you. So you've got to use CPU to do the multi-core optimizations to make everything run faster. At a certain point, sometime in the future, it's thought that we're going to add so many cores that the cost of coordinating all these cores is going to be more than the gain you'll get back. So that's definitely one thing to watch out for today is, are you spending more performance on trying to get your data into these chunks, to get them on all these different cores, than it would be just to run the computation on one core? And the thought is that eventually, if we keep adding more and more cores, we'll hit a limit where the overhead of managing these cores is just too much. Now, I think back when I was in school, and this number may have changed, I think the number was somewhere between 80 to 120 cores is where we're going to max out. That number may have changed, maybe totally out of date, but there was a number that was once we get to this level, we see no way we can manage this number of cores. Now, GPUs can do it because GPUs aren't quite as tightly managed. You send your data up, you got a bunch of discrete cores all doing their thing, but definitely with CPUs, that was the worry. Portland is where I'm from is a Intel town. So we have a lot of Intel engineers thinking about these problems, and, they would come to talk to us in school and talk about everything they were dealing with. The other classical problem that Intel was dealing with, and they talked about a lot at the time, but kind of solved for now, is that when you have all these cores, and they're all reading from memory, they're all going over the same, RAM connection. So at a certain point, you start to max out because not all these, cores are going to have the bandwidth to talk to memory at once. And for Intel, that was a real problem with the Core 2 Quad, I think was the last time it was a problem, where it was one of their first quad-core processors. And actually, even though you had 4 cores, you didn't have enough bandwidth to actually pull stuff out of RAM fast enough to feed all 4 cores. If you look at more modern machines, they'll use multiple memory lanes. So I think the Mac Pro has 4 memory lanes that it can use all at once. I think it's 4. It's either 3 or 4. It might be 3. But you start seeing these architectures where they're really increasing the amount of bandwidth to memory, because as you're trying to feed all these cores, you've got to have the connection to RAM to actually pull your data out and process it. So that's just another thing to watch out for is, depending on what era machine you're on, you might be looking at trying to max out all these cores, but not have enough bandwidth to actually get your data into the cores. I've never run into that on an iOS device. Again, iOS devices are only 2 cores, so you're not really slamming memory as hard as you could be on a 4-core and 8-core device. But it's something to keep an eye on as processor architectures evolve and we add more cores, is that RAM on the machine has really got to keep up, and if it doesn't, you're not going to be able to get the performance improvements you probably want.
Awesome. Is there anything else that we should go over before we get into the picks?
No, I think that's it.
All right.
I think my brain is full, so I think we're good.
You have to loosen your mental belt.
Yeah, it's a lot of information. Yeah, I feel like this has been really a lot of good stuff, and I've learned a lot today, so thank you.
Awesome. All right, well, Andrew, why don't you start us off with the picks then?
Okay, so I've got a few picks. One of them is, I kind of ripped it off actually from Colin. We were talking before we started recording, and he got himself set up with Shush, and I've never heard of it before, so I went and got it, and it's pretty cool. So this is just a little menu bar app on the Mac App Store that gives you a push-to-talk hotkey for your Mac, and it's nice for something like this where we're recording but want to be able to mute ourselves. And so, anyway, it's like $3 on the App Store. And then the next pick is, it's kind of a competing podcast site, so I'm a little wary about it, but no, I'm just kidding. But it's the Core Intuition Jobs Board, and this is a jobs board that was put up by Manton Reese and Daniel Jalkut, who have a Mac and iOS development podcast together, and I think it's quickly gotten pretty popular. Apple's posting jobs there, and a bunch of other kind of big, well-known companies are posting jobs there, and it seems like they've got a high-quality audience, so it might be a good place to look if you're trying to find a job or if you're trying to find someone to hire. And it actually leads me into my next pick, which is that we actually have a job posting. Mixed Key has a job posting there right now, so we're hiring a Mac developer, and you'd get to work with me. I don't know if that's a plus or a minus, but we work on some really cool stuff, and it's a great work environment, and it's the best job I've ever had. So if you're looking for a job or just looking for a change, check it out. Those are my picks.
You do like music and audio software, right?
Yeah, so we write apps for DJs. So there's a lot of audio processing, a lot of custom UI. We've got a fair amount of MIDI code at this point for interfacing with external MIDI devices, and just a lot of really cool, fun stuff that people use our apps because they like them. not because they have to. So it's fun to work on.
Cool. James, what are your picks?
So I've got one pick. So a few weeks ago, I went to the record store and I picked out some records I was going to buy. Picked up a copy of Led Zeppelin 2. Paid like $15, which isn't a terrible amount, but wasn't sure if it was like, there's so many things that can go wrong with like vinyl, even if it's in a good condition, from the mastering and how it was recorded, just a lot of stuff. And so I looked into it and found out I actually had a pretty old copy of Led Zeppelin 2, not like the really first version that everyone wants, and it's like $200, having been run over by a semi, but kind of one a little bit after that. But if you get into vinyl, you kind of get into how stuff is recorded and how it actually ends up as sound on a platter. But there's people that obsess over this stuff, and they exist at the Steve Hoffman forum. So if you end up digging for vinyl, you can learn a lot about how the record that you bought was recorded and mastered and things like that. Very useful. So I go there quite a bit just to learn a bit about how things were recorded. So if you're an audio geek and get into vinyl or even CDs and like to discuss how things are recorded, check out the Steve Hoffman forum. So a lot of cool stuff.
Plus
awesome.
one.
All right. I haven't really picked these on this show, but I've been listening to a lot of audiobooks lately on audible.com, and it's a terrific resource for me as far as being able to get business information and stuff, since I'm a coder for hire. And I've really been enjoying some of the books that I picked up. I'm going to pick one of those books, and then I'm also going to pick an iOS course that I just picked up. I wanted to check it out. So the book I'm going to pick is The Total Money Makeover by Dave Ramsey. Then I'll put links to both Audible and Amazon so that you can get it in either place. And then the course that I picked up is, I'm trying to remember what it's called. It's by Ray Wenderlich, and he's got a tutorial for iOS programming, and I'm really looking forward to digging into that and seeing what's there. So I haven't tried it yet. I got in trouble a little bit. I had some people complaining that I picked stuff that I haven't tried yet. So I haven't tried it yet, and this is your warning, but it looks really good. So
the future pick.
Yeah. Colin, do you have some picks?
Sure. Yeah. So I've been, traditionally I've been using GitHub, but recently I've been checking out this service called Bitbucket. It's another Git host, but they give you, says right here on their webpage, unlimited private code repositories, which is nice. So that's nice on its own, is that, you don't have to upgrade to a pro account to host your own code. The second thing is the tool is just a lot nicer. The layout's a lot nicer on, they're on their web front end. So I'm enjoying using Bitbucket much more than I have with GitHub. So if you're a Git user, check out Bitbucket. Really great service. Another thing I've been doing is I've been playing Hearthstone a lot on my iPad. They just shipped Blizzard just shipped an iPad client for Hearthstone, and I would not suggest downloading that if you have anything to do or any projects to do, because it is a wonderful, addictive little game that I've been playing. It's actually, I used to play Threes all the time, which is another great app, but now I'm playing Hearthstone. So to take the place of Threes, you have to be a pretty good game. So I've been doing that. And then another app I've been using that I'm actually beta testing right now, it's not out publicly, but their website's up, you can go check it out, is this app called Pixel Winch. It's another app out there that does screen measurements and stuff like that I will not name by name, but there's another popular one out there by a different company that does pixel measurements. You can basically take it to do a UI review and measure the distance between different elements on the screen to make sure everything is lined up correctly. The workflow in this app is a little cleaner, and we've been beta testing it at work, and everybody loves it. It just helps you measure, and it does everything on the fly, and it takes screenshots of your UI, so you have a screenshot to refer to instead of trying to measure everything live on the screen. Really great application. I hope it should be out soon. I hope it is, because I'd like everyone else to be able to use it. But really great app for everybody to keep their eye on.
I've been using Bitbucket for several years for my own personal repositories that are private, and I've always been super happy with it. And it also supports Mercurial, which I consider a plus. So +1.
Yeah,
another +1. Most of my stuff's on Bitbucket too.
If you're behind a firewall, so if you're a corporate user, they have a service called Stash, which I'm looking at right now, and Stash is really great as well. So if you want to host your own on your own server and you have some money to throw out a commercial license, Stash is a pretty great solution.
Cool. All right. Well, we'll go ahead and wrap up the show. Thanks for coming, Colin.
Oh, no problem.
All right.
Yeah, thank you. I thought that was great.
Yeah, great stuff.
Hosting and bandwidth provided by the Blue Box Group. Check them out at bluebox.net. Bandwidth for this segment is provided by CacheFly, the world's fastest CDN. Deliver your content fast with CacheFly. Visit CACHEFLY.com to learn more. Would you like to join a conversation with the iPhreaks and their guests? Want to support the show? We have a form that allows you to join the conversation and support the show at the same time. You can sign up at iPhreakshow.com/forum.